Dear students, Fourier series. This is an important concept or important series in having wide applications, as I told you in the previous video. Now, to learn what are Fourier series, we require the idea of periodic functions that we have seen in the last video. In this video, I'll give you two more examples for periodic functions. In the last video, we have seen quite familiar functions like sin x, cos x, etc. Let me take you to two more examples so that you can understand what are exactly periodic functions. After that, in this short video, I'll be giving you the definition of a Fourier series, and I'll give you two homeworks that you have to do and send me through my mail. My mail will be given to you in WhatsApp. So here is the first function, which is a periodic function of period 2. T is equal to 2 here. How it is defined? F of x is equal to x for all x in minus 1 comma 1. For minus 1 and 1, for those values in this interval, we have defined f of x as x. Means, for example, f of minus 1 is minus 1, f of 0 is 0, f of 1 is 1, f of half is half, like that. For all other values, because the entire interval it is like that, but for on the entire line, real line, this is the real line. How it is done? The same f of x is given the value f of x plus 2. So whenever, if you put 0, what you'll be getting is f of 0 plus 2, that is f of 2, is equal to f of 0. F of 0 is already known using this one. So that this function is extended throughout the real line R. If you look at the figure, it will be more clear. Look at this one, from minus 1 to 1. The figure of that is this one. Y equal to x, you know the equation of the line y equal to x. So the function has this segment from here to here. That is extended throughout the real line by cutting this portion and pasting here. This is the pasting and this is the pasting. Then next it will be pasted like this. It goes like that. So we have to know only this much. After that, this is replicated throughout the real line. So that's how the behavior, the periodic function takes place. So if you know a piece, that piece can be replicated throughout the real line. So the function will have the entire domain as R. See, don't be don't be confused to have the notion that this is defined only in minus 1 to 1. No, it is extended up to whole real line. Okay. Now another example. Here also it is defined from 0 to half. Minus half to half. That's how it is done. So the interval minus half to half is our fundamental periodic interval. Then the entire real line has got this one. What is the length of this interval? It is 1. Half minus half, this is 1. So in this interval, it is defined like this, and it is defined throughout the real line using this equation g of x plus 1 is equal to g of x. Graph will give you some more things. Here you see from minus half to half, this is the figure that is cut and paste here. So 0 will be replaced by 1, then see 0 will be replaced by minus 1. What is the next thing here? It will be minus 2, like that. So at minus 2, the same function at 0. So what is the value of 0? 0 has, it is defined like this. At 0 is 1. For all values in between 0 and half, it is 1, 1, 1. And for all values between minus 1 and half, minus 1 and 0, this is minus 1. So only two values. This is plus 1, this is minus 1. Plus 1, minus 1, like that it goes. So just go through a few more examples from your text. Then if f of x is a periodic function of period 2 pi, this is how the definition goes, the definition of Fourier series. If f of x is a periodic function of period 2 pi, defined in R with this equation f of x plus 2 pi is equal to 2 pi. Here the period, that's a special period, general Fourier series we'll learn after learning this one, because this kind of function, which is periodic function of period 2 pi, is very special. Then if you define like this, its Fourier series is defined. Its Fourier series is given as a series, infinite series, given by f of x is equal to means its limit. Okay, I'll tell you what exactly it is. F of x is equal to some coefficient a0 by 2, which is a constant corresponding to this f of x. Then an and bn, these are called Fourier coefficients. So let me read it out. F of x is equal to a0 by 2 plus sigma n equal to 1 to infinity an cos n x plus bn sin x. That's what we call it as Fourier series of f of x. So it's a trigonometric series having cos and sine. If you expand it, what do you get? If you expand it really, you will be getting a0 by 2 plus, if you put n equal to 1, it will be a1 cos x plus b1 sin x plus etc. It goes like that. Second one will be b2 cos 2x plus a2 cos 2x plus b2 sin 2x, etc. So this is important. This is what we call it as Euler's formula for finding Fourier coefficients. A0 will be calculated using integration. Integration must be thorough to you, then only the problems can be done. A0, it is 1 by pi minus pi to pi f of x dx. An, the Fourier coefficient I told you, which comes along with cos n x, is computed like this. An and bn is equal to 1 by pi integral minus pi to pi f of x sin x dx, sin nx dx. This is to be remembered. So this formula is better known as Euler's formula for computing Fourier coefficients. Let us, before deriving Euler's formula, we have to derive it. Let me ask one question. These are homeworks. How to find integral minus pi to pi cos mx into cos nx, where m and n are integers from 1 to infinity. And similarly, what is the value of integral minus pi to pi sin mx into sin? So the knowledge of these two integrals are essential. As you know integration from your plus 2 classes, you must be aware of that one. Then only we will be able to derive Euler's formula for Fourier series. So once again, let me wind it up. This is your Fourier series. When f of x is a periodic function given to you, it can be expanded as a0 by 2 plus a1 cos x plus b1 sin x plus a2 cos 2x plus b2 sin 2x. These are to be computed. A0, a1, b1, a2, b2, etc. are to be computed with the help of Euler's formula. So we'll have it in the next class. Thank you for watching this video.